Okay. So anybody in the class who would like to give it a try, tell me how we can do this. I have started recording this session as well because like last session, I want this to be available for you to review later on as well. So anything that we do. So basically in this question, you've got two things. So for the question on the outset looks very similar to the question that we did before the midterm, right? But there are some minor additional details, right? So for example, the overall bar is the same, although I've specified now a specific material, ASTM A36. So this is a kind of a design example. Again, when you start from scratch the design, you basically have to um, let me actually have the recording on a second device as well, because sometimes the primary device, if that fails, then I don't have a backup. Okay, so in this design question, which as I explained is very similar to the midterm question, you have sorry, before midterm question, one of the tutorial questions. What you have is a bar supported with connected to a bracket through a pin connection. And right now we are interested in the design of the bar, not the bracket, but actually the bar. But similar concept can be applied for the design of bracket as well. So in this case, what I am asking you to do is, given the material and the geometry dimensions are known, right? You have to find out the maximum design load or allowable load for this bar, considering all the factors such as the failure of the bar, maybe due to the axial stresses, or the failure of the pin due to the shear stresses. Now, before the midterm, our approach was to find out, for example, the gross stress, the net stress, and the bearing stress in the bar to determine if the bar will be safe or not. And we used the stress which was the largest to guide our choice of allowable load, right? So that's the approach. And as far as the pin was concerned, the primary mode of failure is shear. So therefore, we considered the shear failure in the pin. And if the pin was safe point, the point of view of shear, that was then acceptable, right? Again, in the early stages of design, you may have other things like, thickness and diameters also not completely specified. But at this stage, but again, you have to start from somewhere, right? Unless you take a multi-objective approach, which I told you is probably slightly beyond what we are going to cover in this course. So we are not simultaneously going to have all the variables as free variables. So we'll look at one of the variables at a time, and then we take a kind of iterative approach to improve the design. So let's say as your initial guess, you have settled with these dimensions that I have given you in the problem, and the material that you want to make it out of is ASTM A36. From that, you are going to calculate the allowable load. Then you will see whether the allowable load is based on reality, the kind of load that you want this hanger to support. Is that good enough or not for you? Okay, so that's what we are trying to do. But then I also want you to use the knowledge that we gained in the last lab session, which was for the finite element analysis or the SolidWorks, to validate your hand calculation results. Okay. Now, there can be two approaches. One approach is you completely use the approach before the midterm and try to design, right? That's the easier approach, but you understand that there may be some inaccuracies because you are not considering stress concentrations, right? So you can take that approach, or you can take the approach with the stress concentration charts included in your design as well. Okay, so let's try to do this, and let's, because we have now covered the topic of stress concentration as well. So I will also account for stress concentration in my hand calculation, and then I will try to complete the design first using hand calculation, and then I will try to do the same design but using finite element analysis. So this can be very useful from the point of view of your project, you see, because in the project you have got similar kind of problem. You have a bracket that you are designing to support certain loads, first using hand calculation procedures, and then you are going to verify using the FEA, right? Finite element analysis. So essentially, we are working on the same lines, although obviously for your project, you have to do a number of iterative steps to come to your overall final conclusion. So let's now quickly try to see the data. I will also actually open this over here. So, and again, you can have it open separately on the other side as well, so that, and I will move this on this screen so I can keep on seeing the question statement and I don't have to constantly scroll back and forward on my small screen. So, to solve the part A, you see, let me just lock this, right? Okay. To solve the part A, essentially what you have to do is you have to first of all look into the important kind of stresses. So first of all, considering uh, sorry. So considering the bar failure modes. Okay, first of all, I will look into that. Then I will look into the pin. Okay, and then I will calculate the failure. Now, I will ignore the gross stress in this case, but I will still evaluate it later on because I know that the gross stress will be smallest. Yeah. So, gross stress in this case will be smallest. Now keep this in mind, it may not always be smallest if, for example, the area is later on reducing for the same bar, right? And then that may, you may have to evaluate that exactly. So you may have to look into that as well. So gross stress in this case will be smallest. So we can ignore that. But for completing the argument, I will evaluate that as well. Okay. Now, again, I don't think I will to. So let's now try to look into, first of all, the sigma gross in this case. So based on the gross stress, oh, sorry, you should have told me that you cannot see my screen. That's bad. Do you want me to cast it on your screens, or is it okay to just show it on the, I think I can just show it on the board. Right, now you can see it, right? So can I move it, actually make it full screen? I don't know. Maybe that will make it easier. Okay, right? This is slightly bigger. Yeah. So first of all, let's look into the criteria based on the gross stress. So we will say that the sigma gross should be less than equal to sigma allowable, right? Now, what is the sigma allowable in this case? That's our first question, isn't it? So sigma allowable is equal to sigma yield divided by factor of safety. Okay. So now sigma yield in this case is how much? You have to look that up for ASTM A36. So you can go into a material database and look for ASTM A36. Or in this case, because I will later be using SolidWorks for the analysis, I can quickly look up the SolidWorks database, right? So that I am using the same values. Okay. So in this case, if I open SolidWorks, I think if I remember correctly, this was the value in this case is 250, but I'll just confirm that. Okay, megapascal for the yield strength. For the ultimate strength, it is around 400 for the ASTM A36. So let's just let me open that on the separate window. and I will quickly reconfirm the number. So for now, I've given in the question, the factor of safety I'm saying should be at least 1.5. Okay, that's what I'm saying. So sigma yield, if let's say that is 250, then this is 1.5. Then in this case, okay, let me now confirm from my other window. So let's say, sorry, it's taking a few minutes to start. I will change the unit system as well. Okay. And now if I go onto the material option here, I can go into edit material like I did the other day, and I can search for ASTM A36. So A36. So ASTM A36 is here. And you can see, like I told you, that the yield strength in this case is 250 megapascal, right? So that's the yield strength. The ultimate is much higher, 400, but because we don't want it to plastically deform, that's why I'm using yield strength as the criteria. Okay. Now, sigma yield in this case, therefore, is 250. So how much is 250 divided by 150? Anybody? Okay, so 166.67 megapascal. Thank you. So, so that's your, sorry, this is sigma allowable. So I should say that this is sigma allowable. Okay. Now, once we have the sigma allowable, we know that we need to keep it below the yield, right? So in this case, the gross stress will be exactly force over area. Actually, I'll just call it as force P, not allowable right now because finally we will work out what the allowable is, right? So P over area. And in this case, the area will be the cross-sectional area. Okay. So which will be the width into thickness. Excellent. Yes. So we are saying that P is equal to width into thickness multiplied by the allowable stress. Okay. So in this case, this becomes, how much was the width and thickness? Yes. So let me move this here. Can you see? Okay. Yeah, I want you to see both screens. Yeah. So this becomes 40 times the thickness. What is thickness? 10 mm. Okay. Multiplied by 166.67. So P should be less than equal to, in this case, how much? 80 newtons, right? So roughly it should be less than 66.7 kilonewtons. So that's our first estimate. Okay. So 6668. Okay. So again, the approximately it will be 66.7 kilonewtons, right? So that's the first estimate that we have. Okay. Now, moving on to the second criteria, which will be, yeah. Okay. So the second criteria can be based on net stress. And this time I will also include the effect of stress concentration, because I know in the region of the net stress, there may be a stress concentration as well. Okay. So first, let's do the net stress using net stress criterion. Okay. And in this case, the sigma net should be less than equal to sigma allowable. Okay. But I will say net stress criterion with stress concentration. So in that case, the criteria will change and this will become K times sigma net, where K is the stress concentration factor, right? So K into sigma net, or in other words, sigma max should be less than equal to K sigma net should be less than equal to sigma allowable, right? So for sigma net, we will now go back to our definition for the appropriate case, because now we have to decide which case is going to be applicable. Let me open up the formula sheet in our other screen. So you can then tell me, or I can use the slides as well from last lecture, right? Because we've got some formulas there, okay? Now, let's say, because obviously I want to kind of give you a slide of a kind of realistic experience. So I will use first the slides. So if I go to my slides that I shared with you. Right. So in these slides, we can see here, we have got the closest case that we can think of is probably this one, isn't it? A specimen with a circular hole inside, okay? Because that is the closest to our situation. So you have to now look for a chart which closely represents your situation. But everybody agrees this is the correct one. So based on the charts that are in the slides, this is the closest case. You have got an axial load, you have got a hole in the center. But there is a main difference here, okay? And the main difference is in this hole, does it say there is a pin going through? Right. Now that means that this chart is actually not going to be 100% accurate, okay? So unless you have a better chart, you can still use it, but you have to note it down that this is the limitation of my analysis. Now, obviously, you can go and look for stress concentration chart manuals in the library, or published charts in other sources like standard bodies, they publish charts as well. If you can find a more closer, that's good. But let's say you can't find the more closer, or you want to have a quick estimate of the design, right? Because later on we will be doing finite element analysis anyways, right? So let's go by this chart for now, noting down that this is a limitation of our analysis. Okay, so we will use this. So I will note down using chart with circular hole without pin as an approximation, okay, for first analysis, noting actual stress may be higher, okay, which will be verified later, okay, through FEA. I do actually have a different chart as well, but I don't want to show you that now, okay? Because because at the end of the day, in real engineering, you will end up in situations where you will not have that relevant chart, right? So I want to give you that experience what to do, right? So take an approximation, make some first educated guess, then move on to the next stage of the design and improve, right? So that's what we do. So which will be verified through later through FEA. Right. So now using this chart, from the definition of the K, what do we need? We need the value of, first of all, we note that the definition of nominal or the net stress is P over T into D minus D, right? Capital D minus D. And secondly, for the chart, we need the ratio small d over capital D. So I will note down these numbers. So we need D over capital D, which in this case is what? It is basically the whole diameter of the pin by the B, what I've called as B in my figure, right? So I will reinterpret my results, and this becomes 12 mm over 40. So this is my D over D. So, Asim, 12 over 40? 0.3. Okay. So this becomes, is there a decimal or that's it, right? Okay. So D over D is 0.3. Secondly, so corresponding to this, the value of the K, we can read from the chart. So we go back to our chart. So we see this is 0.3. So we go up here, right? So we can go up here. So this is 2.35, isn't it? Right? So 2.35 is the value that we will note down. Okay. So I will say that K is equal to 2.35, right? From the chart. Got it? Okay. So now sigma max will be 2.35 multiplied by load over, what was the definition again? Thickness into capital D minus small d, right? So this becomes thickness into capital D in our case is B, right? And small d in our case is diameter of the pin. Okay. So that means now this sigma max will be replaced by sigma allowable in our case, right? So we can say that P should be less than equal to 2.35 multiplied by thickness, which is 10 mm, I think, 10 mm into B, which is 40. Diameter of the pin is 12, right? 12 mm. So this becomes P. Anybody, can you tell me what's the limit in this case? So 40 minus 12, 6. Are you sure? 6, 5, 8. Only this, no 0. That seems a bit too high, too low. Let me recheck. Okay. So 40 minus 12 is 28 into 10. Yeah. Okay. Into 10 is 280. Oh my God. You guys didn't even point out. I didn't even write down the sigma allowable, right? I didn't even multiply it with sigma allowable on the other side. So let me rub this. Let me write this again, okay, properly. That's why this was coming out to be too low. So you need to have a sense of the numbers, right? So in this case, what was sigma allowable? 166.67, right? So we can say that sigma allowable is 166.67 megapascal, right? Uh, so this divided by 2.35, okay, and multiplied by this thickness. So basically, I'm cross multiplying now, right, to get the P. So multiplied by thickness, which is 10, B, which is 40, and diameter of the pin, which is 12. So this completely changes our answer, right? So this should be equal to P. So P should be less than equal to how much? Guys, all the other guys, are you with me, right? Following the procedure, yeah? Okay. So can anybody else check this number as well? Although this number now seems to be okay to me. I was expecting a number of this range. Yeah. Because without the stress concentration, this comes out to be around 46,667, right? With the stress concentration, you divide it with 2.35. So it goes down to 19,000. No, sorry. 40 minus 12 is 28 into 10, right? 280 into 166.67, which is 46,667 divided by 2.35. Yeah, it is. This is not 21. It is 19. Can somebody else confirm, please? Hmm? Okay, I'll do it properly. So I'll write down. So this becomes 46,667.6 divided by 2.35, which is the stress concentration factor. So this should be less than equal to 19,858 newtons, which is roughly, we are saying that it must be less than 19.8 kilonewtons, right? So with this, we have got a second estimate. And you can see how this estimate is much smaller than our first estimate of gross stress. Was that expected? Because the gross stress will be lower because of the higher area, right? Here, the area is smaller, and also we have used the stress concentration factor, right? So that's why we are getting a stress value, load value, which is lower, right? Now, let's now also evaluate the failure because of bearing, right? And see if that becomes a limiting criteria, okay? So, so let's now consider bearing stress concentration. Now, because we don't have a chart for the bearing stress concentration, right? I've not given you any chart for that. So I will basically ignore that. Actually, the bearing stress formula already is written in such a way that it overestimates the stress, right? Because you see, we are not using the full the cylindrical surface, right? We are only using the smaller projected rectangular face, right? So it is already overestimating the stress. So that's why you don't really find a lot of charts giving you stress concentration for the bearing stress. And it's actually also difficult to practically determine because of the nature of the contact. Okay. So again, yes, I'm not saying that there will not be a chart. There may be a chart, but it has not come to my observation. I have not observed such a chart. So that's why I will ignore the stress concentration for bearing mode, and I will only focus on the actual bearing stress. Okay. So I will say ignoring stress concentration in bearing. Okay. As no chart is available. Okay. So now we can estimate the P. Again, we will say that the sigma bearing should be less than equal to sigma allowable. Okay. And in this case, if I move on to the next page, I will have to create a new page here. So I will now say that the sigma bearing is how much? P over the diameter of the pin times the thickness of the bar, right? That was our bearing stress. This should be less than equal to sigma allowed, right? So we can say that P should be less than equal to sigma allowable times d pin into thickness. Okay. So we are saying that this should be less than equal to 166.67 multiplied by 12 multiplied by 10. So how much is this? 20.14. Okay. So let's quickly, somebody can you please recheck? Okay, 20,000. So this is saying that 20,000 newtons. So this should be less than 20 kilonewtons. So basically, in this case, considering the bar failure modes, I'm not talking about the pin right now, talking about the bar only. So considering all bar failure modes, which stress you think is the allowable then out of these three values? Come on. Which one is the allowable? Hisham? Oh, Hisham is no longer here. Okay. Fahim? No? Asim? The biggest will be the allowable. If you put 66 kilonewton, what will happen to the hole near the area where the pin is passing? It will fail because it cannot handle more than 19.8. So in this case, you'll go for the smallest, not the biggest, right? So which is the net with the stress concentration? Ali, are you with me? You seem to be busy with something else today. Okay. So basically, we have got the load allowable is the lowest one, right? Should be 19.8 kilonewtons. So this is the lowest acceptable. If you put any higher than this, then obviously it will fail in the area of the pin. That's what we are considering. And the mode of the failure will be basically a crack because of the tensile crack because of the interaction between the hole and the pin, right? Not under the bearing, rather through the because of the net stress there. Okay. So this is the allowable. And so shear is separate. I will now talk about the shear because that's for the pin. I was right now only talking about bar, right? So I was first talking about bar. Now I will talk about pin. Okay. So yes, this is right now without the bar. Okay. So that's why I wrote here, you see, all bar failure modes. Okay. Because right now we are doing both, but in many practical cases, there may be somebody already specifying the pin, right? So you may be just looking at the bar. So right now we are doing both. Okay. So now considering pin failure in shear. Okay. So what do? We will say that the shear stress in pin, tau pin, should be less than equal to tau allowable. Okay. Now, in reality, the material for the pins, again, most of the time you will be following certain standards. So, for example, we often follow the automotive standards for bolts and pins, right? SAE, Society of Automotive Engineers standards. Okay. Right now, to keep things simple, I'm saying it's made out of the same steel, A36. Okay. This is purely for keeping everything simple in the classroom. Okay. So I'm saying because I will then have to go and check. The problem is that with this kind of an analysis, with the pin right now will be slightly complicated because if you go and you check that material properties, what you find out if you go for the A36, okay, you will not have the shear strength listed here. Can you see that? There's no shear strength listed here. Okay. And this is not an uncommon thing. Most of the material databases will not have separate property listed for shear strength because it's not, you see, each of these numbers that you are seeing on the screen has costed a company something to get this number. They have invested on testing, repeated testing, making sure. So testing is an expensive process, right? And again, testing for pure shear can be slightly more difficult, right? So most of the time we use empirical estimates. We use basically failure criterias. Now, I've not yet fully introduced you to failure criterias because before I do that, I wanted to talk more about, concepts like transformation of the stresses and principal stresses. So once I start my topic today in the lecture for torsion, I will start talking more about the failure criterias. Okay. But common criteria for metallic failure, which is conservative, which means it's on the safer side, is called Tresca criteria. Okay. Based on the Tresca criteria, so I will say using Tresca criteria, assume, so basically if you use Tresca criteria, you can say that the tau yield is sigma yield over 2. Okay. Like I said, right now I've not explained the basis, but inshallah, in next few lectures, we will go through the mathematical basis for this criteria as well. Okay. So using this criteria, I will say that then the tau yield will be sigma yield, which is 250, right? We already know that from the database, divided by 2. So it means it is 125 megapascals, right? And the shear yield in this case, shear allowable in this case, therefore, will become, because we are using the same factor of safety, isn't it? So tau allowable will be 125 over 1.5. So how much is this now? 83.33 megapascals. Okay. Is everybody clear about what I've done and the assumptions that I've taken? Right? So now using this, you can calculate the allowable load based on shear criteria, right? So based on the shear criteria, as I've already said, tau pin should be less than tau allowable, right? So tau pin is equal to load over pi T pin squared over 4, right? So this should be less than 83.33 megapascals. So that means our allowable load should be less than equal to pi by 4. And now what was D? 12, right? Square multiplied by 83.33. So this should be how much? 9,460. So I'll just call it 9,460 newtons. 16. Okay. Can anybody else check this number, please, as well? Because I don't want a calculation mistake. Talal, can you check this if you have a calculator, or Ali? Okay. Yes. This one? So this is what I explained to you. We do not have, in the question, we do not have the shear yield given, right? So now, like, we also did not have the normal yield given, right? So for the normal yield, what did we do? We went to the database. In the database, we had the property of the normal yield for A36. Now we have two options. Unless we search more and find from somewhere the actual value of shear yield for A36, right? Which I told you will not normally be available in the databases. Okay. So we use a approximate criteria based on failure theories. Okay. That failure theory which I used is called as Tresca criteria, right? And according to that, you can assume that the shear failure will happen at half the tensile failure. So therefore, I'm using the sigma yield divided by 2. Okay. So that's again the assumption of our analysis. Okay. 9,424 newtons. So that means, in other words, so basically using this, then it is P should be less than equal to 9.4 kilonewtons. So overall allowable will be what? So the overall allowable is 9.4 kilonewtons, right? For the full system. If you are only talking about the bar, even 19 kilonewton is okay. But if you are looking at the full system and assuming that the pin is made out of the same material, then this is our limitation. That is why usually for pin, you will choose a different material which will be stronger. Okay. Because that material needs to be more rigid, right? It does not have, yes, it will make this value high. Okay. So that's what we normally will do in practice. Okay. So we'll try to choose a pin with a higher strength, because otherwise we will be unnecessarily reducing our overall design load, right? But in this case, this is our design load now. Now, we can also evaluate the margin of the safety for the bar now, because for the pin, the margin of safety with this load will be approximately 1.5 anyways. We know, because that's how we have calculated, right? So, but we can reevaluate margin of safety. Again, keep this in mind. The definition of the way I define margin of safety is same as factor of safety. In literature, you also get the value as 1 minus factor of safety, which is also actually the same thing. It's just that it indicates as a positive value rather than a value greater than 1. You understand? That's the difference. But both are acceptable definitions. But for consistency's sake, in this course, based on the book that I'm following, I always treat the same definition as factor of safety, and I don't do one minus. Okay. I know because I saw some students doing that, so I thought I should clarify it. They are not wrong. And if you do that clearly in the question paper, I will not deduct any marks. No problem. But for my own calculations, I'm always sticking with the same definition. Okay. So margin of safety in this case for bar. Now, what was the most critical mode? Then with the stress concentration, right? So then we can use the same load 9.4 divided by 2.35, which is the value of the K. This is the value of P allowable, right? And what was this? Thickness, which is 10 into the, so this is T, right? And this was the 40 minus 12, right? Is that the correct net area? Yeah. So this becomes the B and this becomes the dia of the A. So how much, to calculate the margin of safety, this is basically the stress, the max stress in the bar, sigma max R. Okay. So how much is this number? No, it should be higher because this is kilonewton. So don't forget to multiply this with 1000. Okay. 14.3 megapascals, right? So that's the stress. So now margin of safety of the bar will be what? So now this is verification, but this is verification through hand calculation, right? Right. So margin of safety is sigma yield divided by sigma max of bar, right? So this is the going to be 250 over 14.3. So how much is this? 17. Are you sure with the calculations? So if we had used 19.8, what would be the, I think you've done something wrong there. Let me recheck the numbers. Oh, that my mistake. Sorry. You haven't done anything wrong. I wrote it wrong. So K will be multiplied, right? Okay. For the max stress. You multiply the nominal or the net stress with the K, right? Not divide it. Okay. So that's my mistake. I'm sorry. So let's now, because this was, you see, a lot of time I just do basic sense check to understand if the number, okay, there's a calculation mistake or not. Because basic sense check will tell me that if with a factor of safety of 1.5, I was getting a load of 19.8, I'm only halving that load approximately, right? So my margin of safety cannot go 17.5 times. It can become 3, 3.5, maybe 4, but that's it, right? So this becomes how much? The stress? So now, yes, that's reasonable. Okay. So margin of safety for the bar is 3.17. Okay. And margin of safety for the pin is roughly 1.5. I've not recalculated to save time, but it will be roughly 1.5. Okay, maybe 1.51 or something because we have rounded the number, isn't it? So this becomes 250 over 78.89. So is everybody clear about the procedure? Right? So that's how you will be using this kind of thing in practice. Let's now quickly switch to the computer to try and solve this in SolidWorks, right? And see if we get something similar or we get a slightly different estimate. Okay. So let's now, I will just save this document and I think I will end the Zoom call as well so that, yeah, okay. So after saving this, let me just now disconnect, stop. And right. So what now we will do is we will remodel the same problem that I solved for you using hand calculations to verify our solution. Now, the thing is with a finite element analysis, like we saw last time, you have to specify the load, right? So even if you're trying to determine the allowable load in this kind of software like SolidWorks, there is no direct way of finding that. Rather, you have to kind of incrementally approach it, right? So for example, for the first case, you may just do 1 kilonewton load case. Then you may do 10 kilonewton load case. And then, progressively increase to see if you are getting closer to the actual loading state or not. So it for the loading, it is kind of iterative for the SolidWorks. Okay. There are other dedicated design softwares as well, but right now we are not looking at those. Now for this particular case, we are mainly going to use it to validate our hand calculation results. So this is our aim today. So we will again model the part first of all. In this case, I can model the part by simply sketching, again, so the easiest way to sketch, again, you can do this in 10 different ways. I'm just going to go through one way which I find easy. So I'll first of all need to select the plane because I want my bar axis to be along x-axis. That's and the bar height to be along y-axis. That's why I'm choosing the front plane. Okay, so that's the logic of choosing the front plane in this case. So I can now put my bar, this is the origin, so I'll just drag it and draw it. Again, I don't have to draw it precisely to begin with. I can always draw it approximately, and then I can use smart dimensions to give it the required dimensions. So the y-axis, what was the height of my member? It was 40, right? So it was 40 mm. So I'll just type 40 mm here, and it will adjust it accordingly. Now the length in this case really does not come directly in our analysis because we are not looking into compressive buckling, right? So in this case, it can really be taken anything, but because in the problem I have given you already as 120, right? That was basically, when I was choosing that, my only objective was to keep the length almost 3 times the width so that the assumption of having an axial member is satisfied. Okay, so that was the thing in the back of my mind when I chose 120. Yeah, but 120 is the kind of the lowest that you would want it to be, right? So that's why I'm putting here 120 in this case. So 120 mm, and it will not significantly affect the results. Okay, now so with this the basic bar geometry is there, but we also need a hole in the member for the pin, right? So I will select a circle to draw my hole. Initially I can just place it anywhere and I can put it any diameter. Then I can go here and I can set the coordinates. Now as far as the y coordinate is concerned, we want it to be in the middle based on the diagram, although I have not specified the exact location, but it will be logical to have the center of the pin aligned with the center of the bar, isn't it? So I'll put it in the middle. So I'll move it to 20, right? Okay. As far as the x-axis is concerned, it can be again at different locations. again, I'm not giving you in the problem any specific place, but based on a rule of thumb, you should typically have the edge away from the edge of the hole that you draw, make in such parts almost 1.5 times the diameter. Okay, that's again a rule of thumb, not a definite guide, but it's a general practice to avoid unnecessary stress concentrations around the edges. So here if I do 1.5 times the diameter is 12, so it will be 18. So 18 plus 6 will be 24, right? So the center of the hole will be 24 from the x-axis. So that's how I will do that. So now the hole diameter should be 12. So I will put the sorry, this is the radius, so I need to make it 6, right? So 6 is the radius because the hole diameter is 12. Is this correct? Yeah. Yeah, it is radius. I've just hovered on it, so it is saying that it is accepting radius here. So with this I can now this seems to be very small, looks very small. So let me recheck that using the dimensions. Okay. Okay, fair enough. Yeah. Okay. Right. So now once we are happy with our basic sketch, we can simply do thickness extrude to basically get our member. So for that I will go into feature and I will extrude it, and I will extrude it along the z-axis, right? So it's a simple extrusion that will allow us to generate, and the thickness by default is also 10 mm, so I'm using the same, so I don't need to change anything, and I'll just say okay. And now I've got my hole and the member. Again, now I have several options to take things from here. A more detailed analysis at this stage will separately model the pin, right, and then create an assembly, right? But for many practical analysis, we don't really need that level of detail. Actually, using that level of detail can even cause more confusion in the design, because then you will have to answer questions like how accurately I am modeling the contact conditions between them, right? Because then the contact you have to define what kind of friction is there, what kind of surface is there. So all of those things will then affect. So normally for initial design, definitely we don't need to go into that level of detail. So what I will use is, I will later on apply certain constraints on this hole directly to mimic the behavior of the pin, okay? And again, with the assumption that my pin failure is already being fully defined based on the simple shear criteria that I have used. Okay, so with that assumption, and then we will analyze the bar purely. Okay, I can create a separate model for the pin and subject it to direct shear. That's also something that I can do to simply test, but again, we really don't need to do that, because that's a very we are using the most basic simple formula for the pin stress anyways, right? So that's why we expect that to be correct. Right. So let's now save this part. First of all, let's actually give it a more reasonable name. So I will rename it, and I will call this as why it's not letting me rename it. Okay, so let me just save it as, and it will allow me to rename my part. Yeah, so I can call it I will actually save it in my OneDrive. Okay, so because this is only the bar, so I have just saved it as it. Okay. Now with this, I will again now follow the same processes as I did in the last lab. I will have to now set up my simulation. Again, I will not spend too much time explaining because otherwise I will not be able to finish. So I'll just go through the process quickly. So going on to simulation, clicking on the study to start a study, noting that we are doing a static simulation. So I will choose the static option. In the name, I will give it a name. So I will call it as bar with so bar pinned. Okay, so I will call it as bar pinned, and because in the start I will use course mesh, so I will just call it as course, and I will just simply give this name. Now with this, first thing like I did yesterday, not yesterday, day before yesterday, was to apply edit material. In this case my material is A36. So ASTM A36 is the one that I will use, and I will apply that on my member. So that's already been assigned. Okay. Now after assigning this, I can now I have to now constrain it. Now this is interesting because how you constrain this, you can use different options. Okay. Now for example, if we did what we did last time, right, we used a fixed geometry, and because the pin is passing through it and then it will be fully tightened with the other member, right, I can say that it's fully fixed at this location, isn't it? Because obviously I'm ignoring the rotation, because if I start looking at the rotation, possible rotation, then it's no longer a static problem, isn't it? So I have to consider the static snapshot, which will only be possible if this is fully fixed in the through the pin, right? So I can use that, and if I use that, then I can basically just simply fix all of this surface, right? And this can be one easiest way of fixing it. But later on I will show you this is not the best way, because it does not really mimic the interaction the pin is going to have. Okay, so this will underestimate our results even for the bar. Okay, so let's try to do this, and but first I will do this just to demonstrate. So I will say okay here. So I will say bar, so I will call it pin fixed, okay, in the name, just so that I can remember that what conditions I used. Okay, best thing is you should have a Word file open in which you write down first analysis is this, second analysis is this, so you don't forget the details. Yeah. Pin? No, there is no previous video for this analysis. This is something which I am just doing live in the class for you, and I am recording the video now. The video that is there is for the last lab that I did. Okay, it's not for this one. So this video will come up later. Yes, I know. That is also, but that's a different analysis, not this one. Okay. I'll have a look at that later. I can't even know which one you're talking about, so I'll have to come and look. Okay, but let me finish this one first, right? Okay, guys. So so now what's the next step? The next step is to apply the load. Okay, so let's now quickly apply the load, and again the load application in this case is very simple. All the load is being applied directly on this edge because it's passing through this. We can have other methods of load application as well, but again right now I want to keep things simple. I will just reverse the direction because it's not compression, it's tension. So this is the direction. And now again, if this was a purely, let's say if you had not done hand calculations, then you can start by applying just 1 Newton load and seeing if the stresses exceed the yield or not, right? And then keep on increasing by running this analysis a number of times. But because right now I'm doing more like a verification analysis, so I will use the allowable load for this particular case, which in this case was 9.4. Okay, 9.4 kilonewtons. Okay, so this becomes 9.4 or 9,400 newtons. Okay, so that's my verification load. So that's what I have put over here. Then after this I need to of course mesh it. Okay, now again this I can go through the whole process again of the mesh convergence and everything. But because this is a very similar kind of structure like the last, the only difference is there the holes were on the sides in the form of notch. Here it is in the middle. So I expect similar sort of behavior. So what I will do is I will just directly start from my mesh control option. Okay, so I'll use a standard mesh. I will already initially just mesh it using a coarse mesh. Okay, and I have chosen, sorry I didn't show you, I have already chosen a high quality because there is no point running this in the draft quality for this analysis because it's a small part. Okay, so I have done that. In the definition I use a standard coarse mesh. Okay, so that was what I did. So now after this, or did I use I think by mistake I use a default. Let me go back. Let me create again mesh quality. Yeah, high, and then moving it to coarse and then selecting it. Right. So you can see now this is a fairly coarse mesh. If I run this, I don't expect the results to be very accurate from the point of view of the stress concentration. So but because I want them to be accurate, so what I will do is I will apply my mesh control. So I will apply my mesh control, and this time I'll just accept the default A to B ratio of 1.4, and I will basically apply the mesh control towards the fine side. Okay, so I will make it very fine near here, and then I will apply the mesh control on these edges and the edges over here and this surface, right? So this will allow me to have a refined mesh. And if I now mesh it again, okay, now you can see it's very refined near my hole and it's coarse otherwise. Okay, now I can run the analysis for the first time to get some idea about my results. So I will now run the analysis. Now first of all I should note if the shape and the things appear as I am expecting them to be. So if I look at this, you can clearly see that the part is becoming elongated and it is reducing in the size equally from both sides. So this is actually kind of what you will expect, right? You'll expect this side to be under tension. So overall the shape looks okay, but we have to keep this in mind first of all, that the deformation scale factor here is very high, right? So it is what, 1028. So it's not realistic deformation scale factor. So you can fix it if you want, but more importantly, this one is a von Mises stress plot, right? And I told you I have not yet discussed with you what von Mises stress is, so I'm not too much interested in looking at this anyways. So what I will do is I will just save the analysis so that it doesn't I don't lose anything. I will right click on the results and I will basically plot the quantity which I want to use for my sanity check, right? Remember I told you first step should be sanity check. And what is the quantity that I can compare is number one, the stress, right? And in this case the stress through my hand calculation, which I know most reliably, will be based on gross stress measure, right? So I did not do this calculation yet in the hand calculation, but we can do that very quickly right now to check this. So let's now plot stress, normal stress along x-axis. That's our component we are interested. I'm using the units as megapascal. I will ask it to do it on a true scale factor so that it doesn't show me a very strange looking shape. And I will go on the chart option, ask it to show me maximum and minimum as well. In the units I'm using floating measures rather than scientific to make it easy for me to read. And then once I've done that, I'll select OK. Now you can see it has created for me the chart of stresses along x-axis, and you can see here is the maximum stress, here is the minimum stress, but we are interested in gross stress. So gross stress will be where? Somewhere along this region, isn't it? Right? So this is the gross stress value, and this is coming out to be around 23.468. Yeah. So can we now compare this using hand calculations? Let's do a very quick hand calculation of the gross stress for this case. So So what was our, so sigma gross in this case will be so what will be the sigma gross? It will be the load P over BP, right? So this becomes, load was how much? 9,400 newtons divided by B is how much? 10? No, sorry, 40. And thickness is 10, right? So can somebody tell me then what's the answer? So 9,400 divided by 400. So 23.5. Are you sure? Everybody else? Okay. So it is 23.5 megapascals. Okay. So now this is the number that we need to use to verify. And can you see here it is 23.468. So there you go. This verifies, this is the kind of sanity check that tells me that my model is not fundamentally wrong. There is nothing fundamentally wrong in the model. Now, whether the stresses near the hole, are they being captured accurately or not, that's a different thing. We have to look at that with more detail. Let's also get the maximum stress estimate based on our chart that we had, right? So let's do that as well while we are here, so that we can, although I already have the margin of safety that I can use that, but that will be like a two-step process. So let's just first of all validate the stress directly. So in this case the max will be K times P into thickness into B minus D thing, right? So that's what it is. So you have got the thickness is 10. So can somebody, I think we already calculated this number as well previously. So this will become 40 minus 12, and yeah, this is, we already have this number. So this is 2.35 into, so I think this was 78.3 89. Okay, 78.89 megapascal. We use this when we were calculating the margin of safety for the bar. Okay, so this one topper, yeah, it will make some minor difference. Okay, but now can you do this for 9400 please? So that we, it's the same number, right? So 78.89 megapascals, right? So I'm taking the lowest estimate, ignoring the decimals, right? Because the allowable, right? So now with this, we have to compare the maximum over here. Can you see here the maximum according to our FE analysis is coming as 67.9, which is smaller or bigger? Smaller. So that means the way we have applied the boundary condition may not be. Now, as you can also say that, well, maybe the mesh is not converged, but to be honest, I've already refined the mesh so much, it's like 0.9 near that hole, right? It will be very difficult for me to even go further down in the mesh. You can try with different meshes to see if the values converge, and I'm quite sure that the values will actually now kind of converge around this number. So the main problem here is how is there a better way of applying the boundary condition or not, okay, even with the same mesh. So today I'm going to demonstrate, because I don't have the time to now run it with several meshes and demonstrate, but I can still show you the other way of applying the boundary condition. So with this, then it means that, okay, yeah, we can by the way, we can always go back and check, because we already know the yield strength, so we can divide it with the yield strength to get the margin of safety. So if we were to calculate the margin of safety based on FEA, what we will do is we will use 67.929 from the FEA analysis. So I will just write it down for you guys. So I will say MOS sigma max from
So I will say sigma max FEA is equal to 60.37 megapascals. So this is for the case 1. Okay, and what was the name of my case 1? Bar pin fixed course. Okay, so that I remember, bar pin fixed course. Okay, actually I shouldn't call it course, I should call it control, because I already refined it, right? So I'll call it control here, and I will change it to control here. Okay, right. So now with this analysis, let's now rerun this, and we can also calculate the margin of safety based on this. So MOS will be sigma yield, isn't it? So MOS will be sigma yield divided by sigma max FEA, which is going to be 250 over 67.378. So this is the margin of safety, which is going to be how much? 3.7. Okay. Now this is higher than hand calc, right? Okay. So let's now rerun the analysis, case 2. Okay, and this time I will, instead of fully fixing it, I will say bar pin, and then let me actually first do that, and then I will give it the name. Okay, so copy study and bar pin fixed control. So I will now call it as bar pin latch plus edge. Okay, and then mesh is control still. Okay, so I'm using same mesh to save time. I'm keeping the study still as static, so all the other things are being kept the same. The only thing which I will now change is the fixture. So to change the fixture, what I will do is I can delete it or I can suppress it. If you want to, for future sake, if you want to keep it there, just suppress it and it will not have any effect. Okay, so now what I will do is, in the fixture I will go and I will apply a fixed hinge basically. Okay, and in the fixed hinge basically it's this type of hinge behavior, isn't it? So right now it's this type of hinge which is going to similar. So this is more closer to an actual pin. Now within the hinge you can have a lot of other advanced settings as well, but again I'm not going to change those too much at the moment, because right now I don't have a lot of data about, like, you know, because we can have the hinge, we can make sure that it only slides in one direction, it doesn't slide in other direction. All of those things can be controlled, but right now I want to keep things simple, so I'm just using a standard fixed hinge type of pin inside, and with I'll just select that. Okay, now but this, if you run the analysis now, your computer will throw an error. Okay, why? Because the hinge can just allow it to rotate, and therefore it is not in static equilibrium. So the computer will say, what are you trying to do? You are asking me to solve a static simulation, right? But it's not static. So to do that, we have to also think about, in real life you won't just have the pin. If you really were going to use this bar to hold something, you will have the bolts at the end, right? And those bolts will effectively just constrain these edges, isn't it? Yeah. Now in reality the bolts will always be through some washers, right? So there will be a slightly bigger area, okay? So the actual stresses will hopefully be slightly smaller. But what I'm trying to mimic is the extreme case situation. So I'm just going to say again fixed geometry, and in this case my fixed geometry is just on these edges instead of the whole surface. You got it? So I need this to mimic the effect of the bolt and the washer on both sides, right? So now with these two edges constrained and inside being constrained using our latch, right, or the pin, now we can rerun the analysis with the same mesh. So I will use the same mesh as before, okay, because I've not changed anything. So I will run it. By the way, again, like I did day before yesterday, you can note down the number of elements and do a bit more mesh conversion study as well, but right now I don't have the time to do that, okay. So now with this, immediately you can see here that there is some changes, but let's go straight to the plot that is more important to us, which is the X stresses. So if you go to that plot, you can see here, so now there is only slight difference, which is interesting actually, okay, which is quite interesting because it means that there is actually the fixed surface in this case, because the mesh was already, I think, refined enough, it was reasonably capturing the stress, and according to this the stress is actually less. So unless now we physically model the interaction, I don't think will be able to get a higher value. So let me, I have not modeled, I have just modeled the let me check this, what I have done. I think I made a mistake here. Yeah, I kept the same thing. Okay, sorry, my so I need to delete this. I didn't use the latch. Okay, then this is for the edges, so let me recheck. Yeah, edges are okay, so that's fine, but I think I didn't put the latch on. So fixed hinge, in the fixed hinge I have to select the surface on the face one, and that's it. Yeah, now it's correct, hopefully. Let's rerun the analysis after saving it. Right, so now if we go and we check the stress, can you see the max has gone significantly higher? But again, before I trust this result, what I need to do, I need to do a sanity check, and the sanity check will still come from gross stress, because we know reliably the gross stress. So let's do the probe, put it somewhere where there is no stress concentration, and you see the gross stress is 23.46. So that means that the mesh it's now meeting the sanity requirement. So this increase is most likely the actual that you will expect, right? Because in reality, now like I said, in reality you will have to really consider a smaller area around it, right, to simulate the effect of washer, right, and the bolt contact basically, right, on the surfaces, because it is going, the force will be transferred through friction to the bar, isn't it? So in reality the stresses will be slightly lower, and you can do that. You can actually go back and create a small circle here, right, and then that will allow you to select that surface in the software, and then you can apply that as well, but that will just take me more time. My class time is now almost finished. But what I'm trying to demonstrate here is you can't just go blindly and look into some colors on the FEA software and think that you've got the correct results. You have to go through the process to convince yourself of the authenticity of the results, and then pick the ones which makes more sense. So in this case, actually the margin of safety should be calculated based on this 129. So I will now call this, I will basically use this name over here. So I will call this as what was the name? Pin latch edge, pin latch edge control. Okay, so with this case the max from FEA is how much? How much was the max from FEA? 1. So let me check it again. So it is 129.476. So I can just call it 129.476 megapascals. Okay, this is case 2, right? Okay, and the margin of safety in this case will be, can somebody tell me? 1.93. So this is lower than hand calc but above target FOS equal to 1.5. So design load is acceptable. Right conclusion? Right? Now you may end up in a situation where it goes lower than your design, right? Your target FOS. Then you need to revise. You can then slowly, gradually reduce the load in FEA. So maybe by 100 newtons every time, right? And then until you reach your target factor of safety. Okay, and again these are not going to be very precise calculations for that. Don't worry about if it is 1.5, 1, 2, it doesn't matter, right? You're getting the point. So you can then iteratively, and then basically that's called as design optimization, right? So you optimize, or I can ask you, for example, to slightly change the thickness if you are not able to achieve this, right? You can make the thickness to be 12, rerun the analysis, right? That's what I'm actually doing in question 2 and 3 of that, but we won't have the time to do that, but I've just given them to you to show you the method. I hope everything is clear, inshallah. So I hope you will be able to apply all of this in your project. That's why I'm not asking you to submit this, okay, because I know it is extra work if I ask you to submit this now. So as long as you can apply this, inshallah, in a good way to your project, this is going to be good. And obviously you should always you can always take these screenshots out. For example, you can directly also export the report, but you can also take the screenshots out and then put them in your reports. So I'll stop this at this point. Thank you.